So, welcome to 67th lecture on electrical machines 1, and we have been discussing about DC generator, and DC generator primarily are of two types we have discussed. One is separately excited generator, and another is called self excited or shunt generator, self excited. Or shunt generator. Why it is self excited? You do not require any DC supply, that is, to generate a DC voltage you will not ask for another DC supply needed. That is the beautiful thing about self excited generators or shunt generators. Okay. Now, these are the things. In case of separately excited generator, you have this field winding, okay, and excite it from a separate DC source with a resistance connected, whatever it is, DC source, and you get the generated voltage. In case of and these are the armature terminals F2 field terminals, and in shunt generator what you do is this is the field winding, same field winding F1 F2, connect an external resistance, connect in parallel with the armature, and this will be these terminals. The value of Ra is much smaller compared to the total resistance of the field coil. And we have seen that its open circuit and load characteristics it was like this. OCC of this generator was like this, and but do not forget to mention at what speed, at 10 RPS, say rated speed, and this is suppose the rated voltage, this is the nominal field current, and the load characteristics of this generator will be, load characteristics is always sketched against IA and terminal voltage, that is here I will connect load. Terminal voltage is this voltage V, and we have seen this will be a drooping characteristics. Try to draw more and more armature current. Of course, there is a rated current of the armature beyond which you will not go. So, from no load this voltage will drop, because of no load voltage it is Eg minus IARA minus brush drop, and because of armature reaction also a little bit of voltage drop takes place, and armature reaction aspect I will take later as I told you. But this is the overall thing here. In case of shunt generator, that is we were discussing right now, it will be like this. That is, you have to run the machine as a separately excited generator, and what will be the voltage available under no load condition is decided by, and mind you here I should be also drawing correctly, it is like this. There is a residual field must be there, it will not pass through origin. Even if field current is 0, there will be some little induced voltage. In fact, that is the reason you at the end get a very large voltage. And how much voltage to which this machine will excite, it depends upon what is the value of the field circuit resistance. This is called RF line, which is just the VI characteristics of the field circuit. This is voltage axis, and how much voltage the generator will generate? It will generate across the armature A1, A2, this generated voltage will be about Eg. Is not. To be very frank, this is R A and here is your E G. So, E G minus with this switch open, it will be minus this field current into R A, but R A is very small and I F is also very small because this is very high. So, it is approximately this E G will come. Now, and here also you do not forget to write at 10 RPS. When the machine was, these characteristics I in fact used here, that you must understand to get a feeling of the amount of voltage available from this DC generator connected in a shunt fashion. Shunt means parallel, armature and field windings are in parallels. That is fine. Now, what about the load characteristics? So, I will go to next page. So, it is nothing wrong if I redraw the things once more. So, this is the circuit diagram because that will be needed, and this is your armature terminals and this is your field circuit terminals, and here is the switch where I will connect load. Load means resistive, everything is DC, load resistance, and that is all. Now, the open circuit voltage with S opened, we know what is the voltage developed, that is this is the point of intersection, this much is the voltage. Okay. And in this axis, mind you, this is field current and this is this voltage is the open circuit voltage. When the load current is 0, this current you can easily see this is not a armature current, because here is a junction. Armature current will be here, if I draw it properly, it will be here. Suppose I show this branch also, then it will be much more clear. This is the thing. I will parallel them. This is I L, this is I A, and this is I F, assuming polarity of the induced voltage this side plus, this side minus. Mind you, in case of generator, if you want to reverse the polarity of the induced voltage, E g is equal to k phi n, you can either change field current direction, supply polarity of a separately excited generator. If you reverse, keeping the direction of rotation same, if this is plus, this is minus, then if you reverse field current, keeping direction of rotation same, supply voltage will reverse its polarity. If you reverse both of them, both the direction of field current as well as direction of rotation, polarity of the induced voltage will remain same, because k phi n. Anyway, these are important things, but it should you should be very clear about that. So, this is the thing. Now, this one is called the at open circuit, and what is the load characteristics? Load characteristics looks like I can sketch for load current versus the terminal voltage or armature current versus the terminal voltage. Either of them I can do, because external load current whatever you are drawing with respect to that how terminal voltage is changing, I can find that out. Therefore, if I say that this axis I can sketch IL or IA, and so when IL equal to 0, then the generated voltage, open circuit voltage is this voltage, is not, that is what I will get, terminal voltage here, this voltage, and as I told you this is RA, here is your EG. So, little drop IRA you can neglect or whatever it is. So, it is like this. Therefore, if you start drawing current IL, it is expected that terminal voltage will fall, because EG minus IARA will come into picture, more current IL, IL is approximately equal to IA. So, this can be written as KCL IA is equal to IF plus IL. What I am telling, IF is pretty small, because the resistance of the field circuit is many times more than your load resistance. Anyway, so this is the thing. About one thing I am sure, that is with respect to a separately excited generator, I told you if you go on reducing the load resistance and if by chance a short circuit takes place here, that is 0 resistance, current will be very large, armature current, you recall that. So, for example, here in fact it is there, I will show you. So, this is the thing. If this terminal is shorted, this current will be pretty high, terminal voltage 0. How much will be the current? Very large. What is the order of the current? That generated voltage EG divided by RA, EG by RA if it is shorted. Very large current will flow. Now, let us see that extreme point first in this case. Suppose you will connect a load resistance, next page I think I went, yeah. So, suppose this is the switch, it is connected, armature current is flowing, which cannot now be neglected compared to IL, IA will be of the order of IA, and suppose I make this terminal resistance, load resistance suppose 0, that extreme case let me first tell you. If a short circuit occurs, what is going to happen? How much will be IL? How much will be IA? That is the question. Acha, one thing is clear, if a short circuit occurs, that is RL equal to 0, with RL equal to 0, we must conclude V equal to 0, that is I have shorted terminal voltage. If this voltage is 0, this voltage is also 0, what is the voltage applied across the field circuit? 0. Therefore, field current will become 0. V by RF is the field current, RF is the total resistance. If somebody makes this terminal voltage shorted, these two are, then voltage existing between these 2 points is bound to be 0, and thereby IF will drop down to 0. if IF is 0, how much is the generated voltage? Very little, because of residual field then only residual field will generate the voltage, which is very small, this much, and Eg will drop down to a very low value. Thereby, the current in this circuit will be that small voltage divided by R A. Mind you, this circuit is in parallel with this, that is with short circuited thing, how the things will look like? This is the thing. This is shorted and here is another high resistance path parallel. Therefore, this IL and IA will be same, no current will now pass through this, IA and IL will be same. And what will be the value of this? This is RA, this is EG. EG residual only now. So, EG residual divided by RA will be this current, very little current. Therefore, one good thing is that even somebody goes to short circuit this shunt generator, okay, momentarily current will shoot up, but final steady state current will be very little. See, this was my starting point when IL was 0 and I am decreasing RL in order to draw more and more power out of the generator. And if I go to the extent of short circuiting it, then the final operating point will be here. See, in the load characteristics, what I want to see, how terminal voltage changes as armature current or IL changes. So, one thing I am telling, the other extreme point in this particular case, it is so obvious that I can make it out, this final current, this current will be this E residual, this much voltage E residual divided by R A, this current, and there is no bifurcation of current here, it is shorted. This I A is I L, it will be like this. Now, the question is, in between then what happens? It is like this. So, this is the no load voltage, this point, we say no load voltage or open circuit voltage. Suppose I will increase the load gradually, I have connected some, I am drawing little current from the armature. Then I know this voltage will be equal to E g minus I R A. Therefore, terminal voltage is expected to fall initially, like the previous your separately excited generator. And what will be the reason of this fall? Because of IRA drop, because of brush drop and other things, and because of armature reaction, which of course, I have not discussed, it will not take much time to discuss also, but I will come to that later, but terminal voltage will fall. Therefore, these characteristics must have somewhere bend it towards this side to reach its final destination when the terminals are shorted. So, the characteristics must be of this kind, and we have to explain this, why this happens, I mean like that, got the point. So, load characteristics of a shunt generator will be somewhat like this. It will start with large voltage, then you increase the load current, there will be drops. In case of separately excited generator, it was not like that, it was going like this for separately excited generator. This you must understand. Okay. Now, how to do it? See, it can be done in several ways. You first tell that, okay, I will pass some armature current. Listen carefully. For some certain armature current, what is going to happen I want to see. IA you fix. Then what will be IA RA I can calculate. IA chosen, okay, generator is delivering this much current. Then what will be IA RA drop I can calculate. Okay. Then what I will do, and what is IA RA drop? IA RA drop see, this is the field resistance line. Okay? This is the voltage across the field at any time. So, V plus IA RA is your EG. Getting me? This is V. Suppose you assume, okay, machine is IA is chosen and terminal voltage is V at that time found to be, and terminal voltage is, suppose this is very crucial, V. So, I have chosen IA and suppose terminal voltage is V. If terminal voltage is V, voltage applied across the field circuit is also V, because they are in parallel. This voltage if you fix, then I will say, okay, field current will be this much. That is, I will write here. So, I have chosen a terminal voltage. Suppose this is the terminal voltage. If this is the terminal voltage, this V, oh sorry, this part is also very interesting. So choose a V. If you have chosen V, I will say field current is this much. How much is the generated voltage? Assuming speed remaining same, generated voltage must be this much. From OCC I can read. So, V, then field current must be this much, suppose say IF1, say it is V1, terminal voltage, suppose terminal voltage is V1, IA1 is the current at that time in the armature. Then I will say that V plus IA RA, V1 plus IA1 RA1 RA must be equal to your generated voltage. V1 plus IA1 into RA must be the generated voltage. And what is IRA? IRA is this drop, IA1 RA1, IA1 RA, and I will say, oh, generated voltage is now this much. Suppose I have some idea, okay, if you load it, terminal voltage is bound to fall, there is no doubt about it. Let the terminal voltage be V1, and at that time I find the armature current is IA1. Then I will say, look here, at that time field current is IF1 and the generated voltage at that time is this much, V plus IRA. That is the thing. Got the point. Therefore, if you choose I A 1 and V 1 for that matter, then I will say in these characteristics I can fix up this point, maybe this is your I A 1 and this is your V 1. And this is not surprising, terminal voltage is falling. But the interesting thing is, if somebody draws the load characteristics like this, which I am expecting it has to be like this, we find that this terminal voltage versus armature current is a double valued function. That is, for a given armature current, I will discover, oh, the terminal voltage may be either this one or this one. Is not, I have to think in that way, no other way, because this characteristic somehow has to bend and come here. And then this, for a given armature current, if you draw a vertical line, then two terminal voltage may be there, of which I have taken one V 1 and I 1 R 1. Now, then the question is, what about this point? This point is, maybe it will be here, if you draw whatever it is here, and but nonetheless V plus I A R A is E G. So, this length is also I A 1 R A and generated voltage will be then this much. So, this is once again I A 1 R A. So, to make matter now, after understanding this, I can now from the open circuit characteristics, I can predict the load characteristics of the DC generator look in this way. After understanding this, this is the thing. Suppose what I will do is this is suppose the VI characteristics OCC. This is the field resistance line, this is the generated voltage, and here I will sketch the load characteristics. This is either IL or IA, armature current. Okay. Then what I will do? I will say that generator is loaded, and do not forget the connection, this is the thing. Oh, I am sorry, so that I can show you the armature current as a separate thing, it is always better. So, this is parallel here and this is this. So, this is your IA, this is your IL and this is your IF. Now, what I will assume, suppose the generator is loaded to deliver a current IA. Then I can calculate IARA. Now, listen me carefully what I am doing. IARA I will calculate. Now, this side is a voltage axis and this is current axis, field current in this OCC. Therefore, I know the voltage scale, I know the current scale. What I will do? I will calculate this IARA, and then this part is most interesting. What you do? you cut a length which is equal to this IA array. So, I have assumed okay, armature is loaded to deliver 5 ampere current, 5 into RA I know. So, 5 into RA I will calculate, it will give me some volts. So, that voltage I will cut a length from this, and then I will draw a line parallel to this field resistance line like this. Then I am sure this length is IA array and this length too is IA array. Then I am absolutely clear, okay, if you say armature is delivering so much of current, then I will tell that it can do so at 2 terminal voltages. What is that? This was the open circuit voltage as usual, and suppose you are sketching IA only. So, IA value I have chosen, I will go to that IA value here, and I want to know what are the terminal voltages. Terminal voltages will be this one and this one, because terminal voltage plus IA array gives you the generated voltage. So, one value is very little. So, I will get this point and I will get this point corresponding to this and this, and this I will repeat for all the armature currents I like. Now, the point of return will be a parallel line IA array, which will be parallel to field circuit resistance line, but tangential to this. Then only you will get one value, unique value. So, like that I will go on doing 2 values for another armature current, and you will get this final value corresponding to a line parallel to field resistance line, but touching, not giving you 2 point of intersections. There it is a single valued current. This current is IA maximum, if you call it IA max into RA, and your characteristics will therefore, I will correct it a bit. This is the open circuit voltage, it may be here, it may be there. So, terminal voltage will fall like this, bend here and come at this point where it is V by RF. So, with respect to IA, if you have open circuit and field resistance line at your disposal, then you can predict the load characteristics of the DC generator, shunt generator as well. In case of separately excited generator, this point was like that, it was going to very large current, but in case of shunt generator, it is not like that, it will go reach a maximum value and come back. This armature, this axis can be converted to IL axis. You can show, because this I wrote IL and IA, because I know that IL is nothing but equal to IA plus IF, is not, this is the KCL here. So, what I will do for a given armature, this is suppose with respect to armature current we have drawn, suppose armature current versus terminal voltage, this axis I must write what it is, this is terminal voltage. Therefore, what I will do for a given armature current, I will go I got two values, is not this value, and for this value I know what is the field current, is not for this value what is the field current I know from this curve, because terminal voltage is this amount. Therefore, how much is the field current? This current, from the RF line you read that. So, field current will be known. Therefore, I will be able to tell what is the value of IL then, because IL equal to IF, IA plus IF. Similarly, for that this point. Therefore, I can always map this IA into IL, provided I also add IF, I read IF from the corresponding points. Therefore, this is the story of a shunt generator, where both open circuit characteristics and load characteristics I have explained. Here also from no load to full load. Of course, full load will be here, do not worry about that. I will not go to this extent or things like that. Whatever is the rated armature current corresponding to that, I will get this point only. These points are unstable points. If you short circuit it, it will straight away come here. But what I wanted to tell you, it will traverse perhaps a path like this. Therefore, up to IA rated you will go and it will come here. In case of shunt generator, the voltage drop or voltage regulation is slightly higher, because of the fact, not only because of IARA drop, brush drop, these are common in separately excited generator as well. Armature reaction will be also there, but because of the fact field current also drops a bit. Flux per pole is also reduced as you move from one operating point. Here, whatever is the flux per pole, at this point flux per pole is bound to be different, because terminal voltage decides the field current, which is absent in case of a separately excited machine, because separately excited machine field coil voltage is independent of the terminal voltage of the armature, because these two are separate totally. But nonetheless, the shunt generator has the advantage that you do not require any external DC supply to make it operate. Okay, with this I stop here today. We will continue with this in the next class. Thank you.